In this lesson, we're going to look at some measures that have to do with one variable data sets. In fact, the next few lessons will have to do with one variable data sets. So this first one has to do with what's called measures of central tendency. So the main measures of central tendency, in other words, the middle of a data set, are mean, median, and mode. You're probably familiar with these from earlier grades, and they really aren't much different from what you would have learned back in elementary school. However, we're going to have some formulas so that we can maybe make the process a little bit easier for larger data sets. So let's start with the mean, which is just another word for what you've probably been calling average. It just means that you add up all the pieces of data, all the numbers, and then you divide it by the number of numbers. So add them all up. You can take a look at this first formula here underneath population mean. It would be given here as mu, which is just a Greek letter, is equal to x1 plus x2 plus ... up to xn. And those little subscripts 1 through n are simply telling us that, which data piece we're looking at, the first one, the second one, the nth one, and so on. And so if there are n here pieces of data, then we're going to divide it by n as well. And in this case, they use big N to represent the population, so the size of the population. So again, this is a formula for mean for a population. Remember, a population means everybody, everything. So we could have the population of Canada, we could have the population of the school, we could have the population of your family, whatever. So if it's everything, then it's the population. And so again, we call that mu. So we pronounce it mu, like what a cat says, mu. All right? And again, the capital N signifies that we're dealing with a population. Compare that to the one over here on the right, which says sample mean. It's the exact same formula. The only thing that's different is what the variables are. Now we use x with a bar over top of it. That's how we'd say it. That's how I'd say it anyway, x bar. And we still add up all the different pieces of data. But in this case, all the pieces of data are represented by a small n. That shows us that we're dealing with a sample. So remember, sample is not all of whatever you're measuring. It's a subset of what you're measuring. So if I want to find out information about what's going on in Canada, but I only ask every 10th person, now I'm dealing with a sample. The formulas are exactly the same, but the variables just indicate that we're dealing, whether we're dealing with a population or a sample. So we're going to use both of those at different times. Median is the middle value for a data set. Literally, that's all you have to know. It's the middle value. You do have to be able to deal with how do I find that middle? So the first thing we have to do is we have to put them in order. The values have to be in order. I should say ordered. The values are ordered from, and the data values are orders form. I know what it should say here. Let me just get rid of this for a second and fix it. What it should say is ordered from Now it makes some sort of sense. So they're in order from least to greatest. They have to be in order for this middle piece of data to make any sense. So then we have to consider, do we have an even number of pieces of data or an odd number? If it's an even number of data points, then we take the average between the two middle points. I'll talk about this more when we get into an example, but it is a consideration. Like, what do we define as the middle? Mode is just the most often occurring piece of data. Again, it's just literally see which piece of data comes up the most often, and that's your mode. You can have no mode, you could have one mode, you could have more than one mode, depending on, again, what the data is. The last term I want to talk about for the moment is called an outlier. It's an element of the data set that is significantly different from the rest. So maybe if I was measuring the heights of everybody in our school, and most people were, say, between 5 and 6 feet tall, but we had a really, really tall person who was, say, 7 feet tall, that person would be an outlier. So he or she is obviously different from all the rest of them. All right, so let's look at some examples. The first one, you're interviewing for an internship at a risk assessment firm. The interviewer tells you that the annual salary for the 15 employees is $73,518.27, which sounds fabulous. The chart below shows the actual income of the 15 employees, so you get to see them, and they are in order. That's going to be important as far as median goes, right? We need things to be in order to calculate the median. If they weren't already in order, we would have to rewrite them in order. So this saves us some work. Determine the mean, median, and mode. Well, since they are already in order, then getting the median is very simple. So let's start with that one. It is the middle piece of data. So for the middle piece of data, we're going to start here in the top left. I'll erase this in a second, but I'm going to go this way. So we got 1, 2, 3, 4. We're going this way, 5, 6, 7, 8. The reason why I'm stopping here at 8 is because 8 is the middle piece of data out of 15. As you can see, I've drawn a line through 7 pieces of data. If I was to draw the line again through here, then there's also 7 pieces of data. Say I was to start at the other end and work my way backwards. There's 7 pieces of data below 33,450, and there's 7 pieces of data above it. That makes 33,450, the middle. So that is how I would identify my median. So let's do a little coloring here. So I'll just do the median in blue. There's my median. All right, so again, this is an odd number of data pieces. So odd number of data pieces, I simply take the one that's in the middle with the same number below or above it. If there had been 16 employees, one more employee, and I had an even one, that's where we go back to this idea of take the average of the 2 middle ones. So let's pretend for a second that there had been one more data piece here, and then that would make, if that was the case, that would have made this one and this one the 2 middle ones. So I'm imagining there's one more in the end. I would have taken the average of those 2 numbers that I just circled. Okay, so the median is 33,450. The mode is the one that turns up the most frequently. Well, that would be these two here, 12,500. And the mean is where I actually add them all up and then divide by the number of pieces of data. When I add all these up, it turns out to be 1,102,772, I believe. I did this ahead of time to save us a little time. Divide that by 15, and what I get is 73,518.27, which matches what I've highlighted up in the original question. So that is where they're getting their mean from. So we got 3 very different data pieces: 12,500, 33,450, or 73,518. All are considered to be measures of central tendency. So the people who run this company are saying that their average salary is $73,000 and change, which sounds great. And yeah, that's true. From one respect, that is true. But if you take a look at the list of what people are getting, 13 out of the 15 people in this company are getting less than that. So it's not like everyone is getting that amount of money. There's just, say, the president and the vice president, or the CEO and the whatever, chief financial officer. They're getting the lion's share of the money, and everyone else is getting a far smaller amount. So I would say, and I wrote this out ahead of time to save a little bit of time, that their claim of $73,000 is definitely questionable. It's a small sample, and it's strongly affected by outliers. So the outliers in this case are the two highest values, which are drawing the mean up higher than it would otherwise be. The median gives a better idea of what the true middle of this data set is. So I'd say that if I was being honest, then I'd say that the average salary is more like the $33,450. And I pretty much answered question C already here. It's the best one because median is not affected by outliers. The mean will be affected by outliers, especially if it is a small data set. When the quantity of data is large, you can group the data into intervals to make them easier to analyze. When the data are grouped into intervals, you can only approximate the center of the data. To do this, we use the midpoint to represent the values in the interval. Each midpoint is multiplied by its frequency. These products are totaled and divided by the total frequency. So here's a formula. This is for grouped data, all right? So if data is grouped, if we just have intervals, as you can see, look at this example here. Just look down the first column on the left. It goes 10 to 15, 15 to 20, 20 to 25, and so on. So these were supposed to be times for quizzes that were written. Maybe there's two people in the first one. Maybe one person took 11 minutes and another person took 14 minutes in this first interval. They both went into the 10 to 15 minute interval. 20 people were in the second interval from 15 to 20 minutes, which means, maybe two of them took 15 minutes. One of them took 15 minutes and 37 seconds. One of them took 15 minutes and 40 seconds. Even that's slightly different. They all go into the same interval. Anybody up to 20 minutes would go into that interval. We don't have the raw data here. We just have what interval they've fallen in. Since we don't have the raw data, that's why we use the midpoint. We say, okay, if they're all in this interval, then we're going to let the middle of the interval represent the actual time that each person got. So this is a formula. It's just really doing the exact same thing as the mean one above. Again, you can see this is x bar as opposed to mu. It could have been mu just as easily, but seeing x bar there, this formula wasn't written down twice, but it's just showing that it could be, this is indicating me that this would have been a sample because of the use of x bar. What do the other things mean here? Well, sigma, this Greek symbol here, means take the sum of something. In other words, add it up. So it's the sum of, and then we have f sub I. So you can see f sub I is here in the table. It's just the frequency. In other words, the number of pieces of data in this interval. And so, and again, I is just, can be 1, 2, 3. So interval 1 would be 10 to 15. Interval 2 would be 15 to 20, and so on. So sum of the frequency times, because when variables are beside each other, then we assume that they're multiplied together. And mi, it's not written in the table, but that would be this, the midpoint of I. Okay, so then we're going to multiply it by the midpoint. And then on the bottom, it's just the sum of the frequencies. So we're just going to add up all the frequencies. So the average is the sum of the frequencies times the midpoint divided by the sum of the frequencies. This table is just, again, a way to make it a little bit easier for us to do our work and see what's going on. All right, so let's do the first row here of this table. The midpoint between 10 and 15 is, I hope obviously, going to be 12.5. 10 plus 15 divided by 2. We're just taking the average of the two endpoints, 10 to 15. The middle between those two is 12.5. And then Fi times Mi means we're just going to multiply the second column and the third column together. So 2 times 12.5 equals 25. And then we're going to do, the cumulative frequency will be helpful for something else, but I'll just write that down. That'll help, something else being the denominator. So we'll get to that in a bit. All right, then we do that for the next row. So what's the midpoint between 15 and 20? Well, it's going to be 17.5. And then we're going to do 20 times 17.5. And that's 350. Now, the cumulative frequency for this one, cumulative means that we're adding it together. So it's the previous one. So it's this 2 here plus the 20 that's in this row. So now we're up to a cumulative 22. So in other words, by the time we get to the end of this row, we've looked at 22 pieces of data. And then for the next one, it's the midpoint from 20 to 25, so 22.5. And then we're going to do 18 times 22.5, which is 405. And then we're going to do the cumulative frequency. We're going to do 22 plus the 18 that are in this row. So now we've got a running total of 40. So to finish this off, we got 27.5 and 275 when we multiply them, and then we add 10, so we're up to 50. We've got 32.5. 5 times 32.5 is 162.5. Add 5 to that, and we get 55. This is the total. So this is what is meant by sigma Fi. So the sum of the frequencies. So we've just calculated the denominator here. That's why we want that cumulative frequency. All right, so now we want to calculate the estimated measures of central tendency in minutes. All right, so the mean as given by the formula up here, let's just write it out again. The mean is given by sigma Fi times Mi divided by sigma Fi. The sum of the frequencies times the midpoints divided by the sum of the frequencies. So we've already got all we need for the numerator in this column here. So 25 plus 350 plus 405 plus 275 plus 162.5. So if we add all those up, what I just circled, then we get 1217.5. And we already saw that the sum of the frequencies was just 55. And that works out to be 22.1. And this was minutes, right? That was our unit. So what we can find out by doing this is that the average time, the mean time for this quiz, for the sample, was 22.1 minutes. To get the median, then we want the middle number. All right? Well, the middle number, so we've got, there's 55 pieces of data. All right? So, again, I don't want to write everything out. I don't want to have to write out I don't have the individual pieces of data, but I could, again, assume the midpoints are the individual ones. So I could write out 25 twice. I could write out 17.5 20 times because the frequency there is 20. I could write out 22.5 18 times and so on. But that's not really necessary. I just need to find which interval the midpoint's going to fall in and then take that midpoint. So if there's 55 pieces of data, so again, I need to take that 55 from before. The way I can find out what's going to be the middle piece of data is it's going to be the 55 from up here. And if we add 1 to that, just for the purpose of, we're just getting the number. If we add 1 to that, so now it's 56, divide that by 2, that equals 28, or 28. That's telling us that we want the 28th piece of data. So if I had written out all the numbers, then the 28th one would be the median, because then there would be 27 pieces of data below it, there'd be 27 pieces of data above it. Add that 1/28th piece to that, that gives me my 55 pieces of data. That's my median. So really all I have to do now that I know it's the 28th piece of data is figure out which interval that falls in. That's where our cumulative frequency is going to come in handy again, because as you can see, looking down the last column, it goes 2, 22, 40, 50, and 55. Well, where does 28 fall in this list? It falls between 22 and 40. So somewhere in here is my 28th piece of data. We know that by the time we get to the end of the second column, we've still only had 22 pieces of data. That means that the 28th piece of data falls in the third row. I should have said row when I said column a second ago. In the third row is going to be my 28th piece of data. Okay, so highlight and arrow, and it's going to fall in that row. Third row. What's the midpoint of the third row? The midpoint of the third row is 22.5. So that's my median. And again, that's minutes. All right, that took a minute or a few minutes to explain, but if you got it, and if you didn't, you should go back and review this. If you got it, it's really simple to do. You just got to sort of wrap your head around what I'm saying, and then getting the median is really quick. Get the total number, cut that in, or add 1 to it, cut it in half. That tells you which piece of data you want. Find which row that's in. Mode is the easiest of all when you've got group data. Just look for the one with the highest frequency. Well, the highest frequency occurs here, that 20 I just highlighted. Get rid of that. So this 20 right here is the highest frequency. It's obviously higher than 2, 18, 10, and 5. That means this interval has got the greatest number in it. So the mode is that row, and then I take the midpoint of that row, it's 17.5. So most people took between 15 and 20 minutes, and if I had to pick one specific time, I'd say 17 and a half minutes. That's the basic idea for that. What potential issues occur when finding these measures for group data? Well, we can't see the raw data, as already mentioned, so we have to use the midpoint of each, and so that's going to be an estimate. It's not a bad estimate, but it's going to be off by a little bit. Okay, graph the data using a histogram. So I got this set up a little bit to try and save time. So we got time in minutes on the bottom. We got frequency on the left side. Remember, we've got our mean of 21. We've got our mean, median, and mode of 21.1 and 22.5 and 17.5, which we're supposed to mark on once we've got the histogram drawn. So between 10 and 15, we saw that there were 2 pieces of data. So 2 pieces of data between 10 and 15. Remember, I make a bar. And as far as the bar goes, it goes up to the frequency. So 2 was the first one. And then the next one, there were 20 between 15 and 20 minutes. So my bar goes up there. For a histogram, we go between these endpoints. So we're going between 10 and 15. We're going between 15 and 20. That's the width of our bar. The bars butt up against each other to show that it's continuous, that there's no distance, there's no gap between these times, between, you know, the first 10 to 15 interval and the 15 to 20 interval. The next one had a height or a frequency of 18. The next one had a frequency of 10. And the last one had a frequency of 5. Here's my histogram. I'll just highlight it to make it stand out a bit. All right, so that's what it looks like. Now it's just to mark the measures of central tendency on the graph. So what did we say? We said mean was 22.1. All right, so find 22.1 minutes on the horizontal axis. And maybe in red I'll do this. 22.1. 22.1 is going to be right about here where I'm doing this red dotted line, right? 22.5 would be the actual dotted line between 20 and 25. So I'm going a little bit to the left of that. That's my mean. And then my mode was 22.5. I'll do that one in baby blue. All right, well, 22.5, if I mark that on this graph, is right on this dotted line. So it's slightly to the right of the mean. That's the median. And then the mode is the most frequent one. That's really easy to see always. If we have a histogram, it's just simply the highest bar. And that was at 17.5. So that would fall right here. So they're not all exactly the same. The mean, median, mode are slightly different from each other. Here are some common distributions. Again, just to save time, I filled in a little bit of stuff first. So we got what's called a normal distribution. A normal distribution is sometimes described as a bell curve. It's symmetrical, all right? That's the main thing. I think there's 2 M's in symmetrical. So, whatever, I won't bother putting scales on here. I'm just going to give you an idea of what the shape looks like. So maybe it would look like this. It's going to have a highest point in the middle, and then that highest point is going to have it's going to be sort of mirror image. So you can, if you look at this, you should be able to easily pick out what the middle of this graph is. Vertically, it would go right down this line here. If we were talking about things like parabolas and that, we would have called this the axis of symmetry. So we could fold it across on this dotted line, and it would look the same on both sides. It doesn't have to be exactly like this to be normal. It just has to be basically like this. What the thing is with normal distributions, though, are that the mean, median, and mode are all going to be in the middle at basically this spot. Again, the mode is obvious. We can see just the highest bar. But the mean would make sense, as with the median. These bars, the area under this curve represents all the different data pieces. So the middle piece of data, since it's perfectly symmetrical, should be right in the middle. And the average also should be right in the middle, because when we do our calculations, it's going to fall there. right? So that's a normal distribution. That's something we're going to come back to and spend some more time on in this course. So keep that idea of a normal distribution in mind. Left skewed. Well, a left skewed one looks like this. Again, I'm just doing the shape of it. And it doesn't have to look exactly like this, but again, it's giving a general idea. For a left skewed distribution, it has what's called the tail on the left. So the tail, imagine, the shape is sort of tailing away. If you're just looking at it, you can see the tail that, imagine it's some sort of creature or dinosaur in its form. The tail is dragging along the ground. So that's the idea of calling it the tail. So the tail is dragging along the ground. It's on the left-hand side. For a left-skewed distribution, the mean is generally going to be less than the median, and that's going to be less than the mode. Again, let's just look at this. The mode is really simple to see. We can quite clearly see that the mode is going to be up here because that's our highest bar. And again, if the area under the curve represents all the different data pieces, imagine trying to break up the area underneath these bars. I'm just going to guess at where that would be, but it would probably break up somewhere around here. So in other words, about to the left of this dotted line I'm currently drawing would probably be about half the area under the bars, and then to the right of that dotted line would be about the other half of the area. That's the median. So the median would, again, it sort of cuts the area right in half. The mean is affected by outliers. So it's going to be pulled down by those very low values in this case. So the mean is going to be to the left again. And again, this is just an illustration. This isn't an actual calculation. So if I were to use some numbers in here, maybe they'd look a little different. But the mean is less than the median, which is less than the mode. That is left skewed. Right skewed is just a mirror image of this. And again, it doesn't have to be a mirror image, as long as the highest bar is basically on the right and the lowest bar is on the left, basically, then that would be right skewed. So my tail is over here on the right-hand side. That's why it's called right skewed. And then things are reversed. Here, we obviously have the mode. The median would be somewhere around here, and the mean would be farther to the right still. Sorry, the mean, did I say that? Yes. The mean would be farther to the right still. Okay, so those are some common distributions. You need to know them. Finally, we're going to look at something called the weighted mean. Weighted mean is very similar to what we've already looked at for grouped mean. So we have this formula for grouped data, right? X bar equals sigma f sub I times m sub I all over sigma f sub I. Well, let's take a look at this formula. And it says mu, again, this could just as easily, it doesn't have to be mu. Again, it could be a sample, so it could be x bar. So don't get hung up on whether it's mu or x bar at this point. We have to pay attention to that for some other things. But take a look at the right-hand side of the equation. Now we have sigma x sub I times w sub I over sigma w sub I. The exact same thing is going on here. We've swapped out f and m in the previous formula for x and w in this formula. So it's going to work the exact same way. We should even be able to read this without me writing it down. The sum of all the x's times all the w's divided by the sum of the w's. What do x's and w's stand for? Of course, that is what we need to know. Well, the x's are going to be just, that's just our random variable. So in this case, here's an example. Calculate the final mark for a student with the following grades. So the random variable in this case is their category mark. So that would be x sub I. And then the weight factor unsurprisingly, is what W is going to stand for. So weighting. You know that your grades for your courses in school have different weightings. Different things are weighted differently. Exams are weighted differently from assignments and so on. So that's just what this idea of weight factor is. The weighting that has been assigned to particular things. If we want to count some things more than others. In this example here, tests are weighted 40%. Quizzes are weighted 15%. So in other words, we're putting more importance on tests in this than we are in quizzes. Almost 3 times as much. So that's the idea. And then we can just calculate again what the different values are. So the values are going to be, we're just looking for x sub I times w sub I. So again, so we're just multiplying 63 times 40 and so on. 2,520. And then we'll do that for the rest of them. Again, I'll fill them in, but you could confirm it if you don't trust me. These are what I get as the numbers when I multiply across the rows. Okay, so there are my my different values of x sub I times w sub I, and the formula is sigma x sub I times w sub I over sigma w sub I. The total here, if I add all of these up, gives me 100%, which makes sense in this case, the different weightings. So if I were to add up all the numbers in this column, that would give me my numerator. So again, sigma means to add them up. So if I add all those up, and again, I've done that ahead of time, so you can trust me or you can confirm it, but I got 6995, and sigma w sub I was 100%. So when we work it out, it turns out to be 69.95, or approximately 70%. So a person with these marks would get a 70% in the course. Finally, assuming the student has yet to write the final exam, what would be the highest mark they could achieve? The highest mark they could achieve with a perfect exam. All right. Well, the exam is worth 15%. Sorry, let me just take this out. So the exam is worth 15%. So if they get 100% in it, then it would be 100 times 15, which gives us 1,500. So mu, in this case, I'm going to swap out this 915 here with the 1,500. So instead, they didn't get 60. We're going to pretend they didn't get 61%. We're going to take away that 61% they got, pretend that hasn't happened yet, and pretend instead they got 100%. So then we can just, when we add that instead, I get obviously a different numerator, and so mu is going to equal 7580, which is the new mark, the new total they get with 100% exam, still divided by 100%, and that means they could get 75.8, or about 76% overall. So we can play what-if games as well by swapping certain numbers out and playing around with them.